From the painted hills of southern Utah, to the sweeping grasslands of New Mexico, to the saguaro forests of Arizona, the landscapes of the southwestern United States are as iconic as they are diverse. But despite the drastic differences in appearance, all of these ecosystems are connected through regional occurrences such as drought, wildfires, and invasions by foreign plant species. The frequency of these occurrences, in turn, is regulated by the availability of water and the amount of precipitation in the region. In the case of the Southwest, that moisture is delivered every summer in the form of a recurring weather system known as the North American Monsoon System.
In the western U.S., these arid ecosystems are all dependent on the annual cycle of rainfall. And so the occurrence of the monsoon system each year brings them all together in a common dependency that ties this macro system functionally and ecologically together.
The United States lies on the northern border of the monsoon, which usually dissipates in northern Arizona. The system develops over the Sierra Madres in Mexico every summer as the land surface warms, causing the warm, dry air to rise and drawing in moist air from the ocean.
As the land heats up, these warm, moist air masses from the Gulf of Mexico and the Gulf of California migrate along to the slopes of the Sierra Madre in Mexico, and then they rise all the way to the top, and then at nighttime that air descends and gets pulled into a nocturnal low-level jet that then migrates north, bringing precipitation into Arizona.
The monsoon has been recurring in the region for millions of years, but the northern extent of the rains has changed over time. Historical evidence indicates that it once ranged far up into Utah, where it was used by the Fremont Native Americans for cultivating maize, a relative of modern corn.
The North American Monsoon Macrosystem is ancient. We know that it's existed for as long as we have records, both paleoclimate records and modern records. But the extent of the system and its intensity varies quite a bit.
Normally, the monsoon down here varies from year to year, but not that much from decade to decade. But as you go further north, it starts varying more on these longer time scales, decade to decade and century to century, and even millennium to millennium. And so that's a very, that's a very interesting phenomenon that's kind of understudied. And we hope to look at this because it has an impact not just on the biology, but also on human endeavor.
Understanding the complicated mechanics driving the monsoon requires collaboration between a number of specialists in multiple fields. Ultimately, researchers would like to be able to create a computer model of the monsoon system, which could be used to simulate how the monsoon may change in the future, and how those changes could manifest themselves on the landscape.
When we talk about computer modeling, we basically divide the world into grid boxes. Then we try to simulate what's happening in each square over a globe or over a particular area, such as southwestern United States. Then in the computer model, we want to include all the physical, biological, and chemical processes we understand into the model. In other words, the models are only as good as our understanding can be about those specific processes.
The complexity of creating an accurate computer model of the monsoon is immense and includes taking into account meteorological variables such as sea surface temperature and wind patterns, biological factors such as transpiration from plants and shifts in vegetation, and long-term trends in climate such as global warming.
The major challenge is that the monsoon is infinitely complex. That what ultimately creates rainfall is thunderstorms at a very fine spatial scale of a kilometer or less. Trying to represent that in the context of a numerical model is very challenging, and it requires both a high amount of computing power and an intimate knowledge of the physical processes at that kind of a scale.
Further complicating matters is the unstable state of the vegetation in these ecosystems. Many areas in the southwest are currently being invaded by foreign grass species. These species are extremely responsive to the monsoon rains and can quickly recover from wildfires, giving them an advantage over native species of grasses.
The North American Monsoon Macrosystem is going to change in the future. It's going to change in response to climate variation, and it's going to change in response to the introduction of new organisms to the macrosystem. One of those changes that's currently occurring is the invasion of this macrosystem by invasive grasses.
These landscapes are now experiencing invasions of plants from other continents. And in particular, there's one called buffelgrass. It's a plant from Africa that was brought in to either feed cattle or control erosion, and it's being spread all over the world. What could happen very quickly, because this is a plant that actually responds to summer rain, which is fairly reliable in this area, is that buffelgrass becomes the dominant plant on the landscape. And so you could end up seeing, idyllic, iconic landscapes of the Sonoran Desert like this one being covered with a flammable grass.
If we had an increase in invasive grasses or any grasses that actually fill in the gaps between the shrubs, then we would expect wildfire to become a bigger part of the system. So historically, when this area behind me was actually a very large grassland, they would have had fires very frequently, and they would have had to worry about wildfire and the return then of the grasses. But now we have very few fires, so actually if we initiated a system where the fire occurred frequently again, we would expect to have very large impacts on the ecosystem properties.
The history of the monsoon is the history of the region itself, and understanding how the storm has changed in the past will reveal major clues about how it could develop in the future. By analyzing various artifacts from the region, paleoclimatologists can learn a lot about how the monsoon has evolved through the years. One major source of information is tree rings.
Here, the tree rings have a unique characteristic that's quite common in the borderland regions of Arizona, New Mexico, down into northern Mexico. And that is, the rings will often form what we call a false ring. We can use the position and the thickness of that false ring to learn about the monsoon and the length of the arid forest summer. So in some years, if you have a really good monsoon, you'll see a really thick band of growth after the false ring. And then in some years, if you got a really failed monsoon, it'll just quit growing right after the false ring.
Analyses of isotopes in tree rings can also provide researchers with clues, such as the primary source of water that was used by a tree in each year of its life.
There are very large differences in the isotope ratios, in particular the oxygen isotope ratios of plants that are growing with summer-derived monsoon rains versus frontal-derived snowpack winter system rains. At this point, we're very confident that we can distinguish between those two sources, and therefore, by looking at tree rings, we're able to reconstruct the importance of one water source versus the other over the history of the plant. By looking at plants that died at different times, we can produce a continuous record, one which is longer than the lifetime of any single plant. So we can go back more than 1,000 years to reconstruct climate.
A rock etching in Fremont Indian State Park in southern Utah depicts what is believed to be a drought and a field of unsprouted corn. In times past, variations in the monsoon could mean the difference between life and death for native cultures in the region. Today, thanks to mechanized irrigation, the effects of a drought may not be quite so severe, but understanding the mechanisms driving the monsoon system holds important implications for a number of fields of endeavor. Whether examining past cultures, creating a modern forecast, or predicting how the region may evolve in future years, the key lies in understanding the monsoon's patterns and the factors that determine and shape its form each year.